what we want to do now is apply our equations of motion to acceleration due to gravity. And that's all about objects in freefall. So we're talking about any object that is subject to acceleration due to gravity. And yes, we take that value as 10. I know that it's more accurately known as 9.8, but for all our work, we will use the value of 10. Your textbook, I think, may use 9.8, so you may see some slight differences when you're working through it. So the only thing we're assuming that is acting on something in free fall is gravity. We are going to ignore air resistance. And so therefore, we can apply our equations of motion formula because this is a situation where acceleration is constant. And of course, famously, it doesn't matter about the mass of the object. When we drop two objects, they will fall with the same acceleration if we ignore air resistance. A couple of conventions when we are dealing with vertical motion, we have a couple of basic ideas, and that is that moving up is positive. So if something is thrown up, a ball, we would say its direction of motion is positive. When it's in falling, then it is negative. And therefore also acceleration due to gravity is negative because as something is moving up, it slows down, but when it's moving down, it's speeding up. So our acceleration due to gravity is considered to be negative. Just if we think back to your work on graphs, if we just think for a second about what would the graphs of these motions look like if you were to, in this case, drop something from the top of a building. And in this case, if the origin is the surface of the Earth, what would it look like? Have a think for a moment and see if you can sketch that first. What would the two graphs look like for a position time graph and a velocity time graph? Have a think for constant acceleration, what would they look like? So if you drop it from the top, it's not at the origin, it starts at the top. And of course its motion is slow to begin with, but then gets faster and faster, so the curve would look like that. And the resulting velocity, how would that change as well? Because the velocity is starting at 0 because it's not moving, and it is negative acceleration. It is moving towards the origin and getting faster in the negative direction. Of course, if I threw it in the air and then it returned to the ground, what would it look like? This time you'd have the other half of your graph. And in that case, the velocity to start with would be positive. And it would start up here and go through the origin and continue. So in both cases the acceleration would be constant. So how do we apply equations of motion? If we just take the simple example of throwing something in the air, how would we apply those equations? So we need to work out things like the maximum height reached, how long was it in the air for, and what's the velocity when it returns to Earth. Again, write down all your variables. What do you know? So when you're throwing the ball in the air, a couple of things to remember: that the initial velocity is plus, in this case, 20. Now what happens when it reaches the top of the flight? Of course, it stops. The velocity at the top is 0. When we throw something in the air and it returns to Earth, it's often best to divide it into two parts: the upward motion and the down. is sometimes easier to deal with. So to find the maximum height, we only consider the up section of the motion, if you like, the upward section. And in that case, we know the initial velocity is 20, and then for this part, the final velocity is 0. The acceleration is -10, and therefore, in this part, I'm trying to find x, or what is x. Which equation would you use for that? So think about your equations and see which one you think. One of the common ones we'd use here would be v squared minus u squared equals 2ax. We've got v, we've got u, and we've got a. So rearranging that equation, x would be v squared minus u squared on 2a. So the final velocity is 0 minus the initial. Now it should be 20 squared. And don't forget that your acceleration is negative. And when you work that out, you get 400 on minus 400 on 20. So your negatives cancel out and the distance travelled is 20 metres, and that's up in the positive direction. The next question is, well, how long was it in the air for, and which equation could you use? And here, acceleration, v minus u on t. So to find the t, v minus u on a, final is 0 minus 20 on minus 10. And that would give us, because the negatives will cancel out, 2 seconds. Careful here with your signs. Clearly, if you get a negative for time, you've made a mistake. So always check your signs, because t cannot be negative. What would the velocity be when it returns to Earth? If it travels the exact same distance on the way up and on the way down, it should reach or return to the same point with the exact same speed. And we can check that. I could use my v equals u plus at just to check, except if I consider the down, consider the downward section, I would have 0 minus 10, and I know it took 2 seconds. I'm left with minus 20. So what you can see here is, while it initially went up at 20, when it reaches the same point on the way down, it is now the same speed but in the opposite direction. Let's just have a look. We've actually drawn those graphs before, so I'll move on from that. If we have a look at this example, look out below. Get it? Look out below. Drops a stone from the top of a cliff, hits the water, and took 8 seconds. So how would you work this out? So again, this is a process. Just go through your equations of motion, write down what do you know first. So the initial velocity is 0. Do I know the final velocity? Well, no, I don't. Don't seem to have much information here. The time is 8 seconds. I do know the acceleration. So what would the height of the cliff be, and which equation would I use? So just pause for a second, see if you can identify the equation you would use. So which one would you use? The obvious one here, I need an equation with x in it, and why this one, ut plus half a t squared is a good one because the initial velocity is 0. So that first bit of the equation becomes 0 plus half times the acceleration, which is -10, and then 8 squared. So when you work that out, you get, and of course it is negative, which is -320 meters. And the reason, of course, it is negative is because the object is falling. So it has moved in the negative direction. So our answer should be negative. What's the speed it hits the ground at? Once again, good one there is v equals u plus at, because that's 0. And of course, if it falls for 8 seconds, accelerating at 10 meters per second, you're going to end up with minus 80 meters per second. So that's just a couple of introductory examples about how to apply your equations of motion to vertical motion under gravity. So it is the same process as before for horizontal motion. Because it's constant acceleration, what makes this easier is the acceleration every single time is going to be -10. And if you drop something, the initial will always be 0. The key things to remember are direction, signs. Up is positive, so don't forget, always up is positive and down is negative.